Thank you for joining us for the synthesis workshop today. We have an exciting talk on enantiocontrolled ring synthesis by Nicolò Tampellini. Nicolò is a PhD student in Professor Scott Miller Group at Yale University, and he will be presenting on enantiocontrolled cyclization to form chiral 7 and 8-member rings unified by the same catalyst operating with different mechanisms. With that brief introduction, let's welcome Nicolò to begin his talk.
Thank you to Synthesis Workshop for the opportunity to present our latest work on chiral medium-sized rings. To introduce our work, I will talk about stereochemistry and stereochemical elements within molecules. For example, when we are introduced to the concept of chiral molecules, we are often presented carbon centers with 4 different substituents as possessing central chirality. That is, the carbon atom is the stereogenic feature that renders a molecule chiral. Similarly, other multi-substituted centers can also be chiral centers, for example in some chiral metal complexes. Conversely, other kinds of chirality can emerge when the rotation around a single bond is hindered, as in the case of ortho-substituted biaryls, where the central carbon-carbon bond is prevented from rotating and therefore rendering the molecule chiral and not superimposable to its mirror image. Another example of this phenomenon is with allenes and alkylidene cycloalkanes. The geometric arrangement of these compounds is such that 2 pairs of non-equal substituents are arranged in a non-planar fashion and are configurationally stable, similarly to how biaryl systems are. We classify these molecules as having an axis of chirality. Conversely, other kinds of molecules are deemed planar chiral when the coordination or orientation of a different face of, let's say, an aromatic ring renders the molecule non-superimposable to its mirror image again. Examples of this are ferrocenyl complexes and some cyclophanes. But what we're going to talk about today features none of these stereogenic elements and starts from the molecule telenzapine. I encountered this molecule during my undergraduate studies and I was fascinated by its unexpected chirality. This is its structure, and at first glance it looks rather unremarkable. But if we look at the substituents of this ring system, we can see that the carbonyl of the amide and the methyl group of the thiophene are in steric clash to one another, and therefore enforce a non-planar arrangement around a 7-membered ring, which ultimately results in a distorted structure that is cup-shaped. These cup-shaped conformations do not interconvert between each other because of the steric clash we just talked about, and therefore are isolable as thermally stable enantiomers. A very interesting fact about this molecule is that its chirality was discovered by accident, and the most active of the 2 enantiomers of the molecule was discovered by using stoichiometric quantities of the enzyme and separating out the most stable complex with the more active form from a mother liquor that was enriched in the least active enantiomer. This kind of chirality, and really the isomerization mechanism between these 2 conformations, can be related to the inversion of some trigonal atoms, like for example phosphorus or nitrogen species, where an umbrella-type inversion interconverts between the 2 enantiomeric states. These molecules that show chirality due to the relative orientation of groups that are kinetically stable and that do not fit into any of the previous categories sometimes are referred to as inherently chiral. This inherently chiral dibenzodiazepine core is also featured in other drugs. For example, UHAH37 is another muscarinic receptor antagonist that is configurationally stable. Another example of inherently chiral medium-sized ring system in a medicinally relevant context is given by the analogs of MK7725 developed by Merck. These drugs were optimized for stereochemical stability around the medium-sized rings, and large substituents were needed to lock this compound in thermally stable cup-shaped enantiomers. In this case, we can identify the major steric clash between the sulfonamide and the tetrasubstituted center of the benzene ring. Achieving configurational stability in medium-sized rings is a desirable trait for drug-like molecules because they can exploit the rigidity to achieve more selectivity in the binding to the specific target they are going after. So, how do you make these heterocycles? Well, usually with condensation reactions that require harsh conditions both in terms of acid, bases, or temperature, or all of the above, and the yields are not always great. I will highlight that these are just some examples from non-substituted dibenzodiazepinones, but the situation gets even worse when you want to make them more substituted to access the chiral ring system. In the second example, we can see this double SNAR approach to make the chlorodibenzazepinone, but then to install the tertiary amide, which renders the molecule ultimately chiral, we need to go in with an acyl chloride from a doubly deprotonated heterocycle, only achieving 22% yield, under these sort of harsh conditions. But why is it so hard to make these systems? Well, the reasons that render them inherently chiral, the steric clash between substituents, it's also what renders these compounds strained and therefore high in energy. You can imagine that stereoselective synthesis of these inherently chiral rings, given the current methodologies, it's quite challenging because of the harsh steps are not easy to reimagine in an asymmetric fashion, not with chiral stoichiometric reagents nor with chiral catalysts. So, how do we approach the problem of an asymmetric synthesis of these? Ideally, in the best case scenario, we would have liked to have an asymmetric step that directly builds the ring, so a cyclization step, that is mild and can be rendered enantioselective with an appropriate chiral catalyst. Our initial approaches to the problem showed us that the choice of the disconnection to make the ring really matters. Let's say that your target is exemplified by this model on the left, and you decide to disconnect the bond between the red and the white moieties. What you get is a precursor that perhaps has an unproductive bias in a conformational sense to sit in a non-productive conformation. And maybe the two reactive groups are far apart from each other, and if you try to react a red functional group with a white functional group, all you get is intermolecular reactivity that only leads to oligomerization. You just make dimers and higher order species. The disconnection you intended in the retrosynthetic sense does not work in the forward sense. Vice versa, if you're more wise about the disconnection you want to attempt cyclization with, you might be given a precursor on the second line here that now has a productive bias, and so the reacting group within the same molecule are very close to each other and are prompted to react in an intramolecular fashion. With the right precursors, we could build ring strain step by step in the precursor and overcome the inherent strain when forming the ring with the facile reaction. Where we attempted disconnection of this dibenzodiazepinone core using one of the red disconnections on the top of the ring, all our attempts failed because when we got some reactivity, even maybe under a mild condition, the reactivity was intermolecular and never intramolecular. So we think the red disconnections put you into the first unproductive situation. Vice versa, the green disconnections, if you're careful about your choice of the amide substituents, can pre-organize the system in the right way and give you an optimal precursor to carry out the reaction you want to do. For example, we reason that secondary amides and tertiary amides that have two aryl groups, one off of carbon and one off of nitrogen, have some interesting conformational properties that balance pi stacking with dipole. So for example, secondary bis-aryl amides tend to prefer a trenzoid conformation where the two aryl rings are not pi stacked to each other, because doing so would create such a large dipole that this is an unfavored conformation. Vice versa, if you have an alkyl group off of the nitrogen of the amide, this functional group preference becomes to sit in a schizoid conformation, where the aryl rings are able to have some degree of interaction and pi stacking to one another, and would place our reacting functional group close to each other. Following this strategy, we decided to synthesize this compound following the N-aryl disconnection from a sulfonamide and an aryl fluoride. That can lead to an intramolecular cyclization to form the dibenzodiazepinone via an SNAR reaction. We put our N-methyl bis-aryl amide at the top to act as our conformational bias for the system to react intramolecularly, and we were very pleased to observe that this strategy finally worked. In a great number of basic conditions, this substrate underwent a clean, mild, and selective cyclization to the 7-membered ring with no trace of oligomers and higher order products. We were able to obtain an X-ray quality crystal of this racemic product, and I have to thank my collaborator Dr. Brandon Mercado for solving the X-ray structure for me. In the crystal, you can see two different enantiomers of this racemic crystal, which are the two opposite cups of the inherently chiral 7-membered ring system. But if we were only interested in the mild syntheses of these compounds, the project would be over. In reality, since we're interested in an asymmetric cyclization to access these products, this is where the project starts. We were pleased to see a smooth transition between the use of stoichiometric bases to the use of catalytic amounts of bases or superbases, and stoichiometric quantities of a reagent to complete the catalytic cycle. In this context, calcium oxide proved to be the best stoichiometric reagent to affect catalyst turnover, presumably because by itself the reagent is not particularly basic and does not induce much background reactivity, but its ability to bind fluoride and form insoluble calcium fluoride species is probably responsible for the easy free basing of the conjugate acid of the catalyst, which is a hydrofluoride salt. Initially, we attempted to tackle this problem with chiral guanidines embedded in peptidyl frameworks. This is a topic of research I had been working in the past, and I had a series of catalysts hanging around. From the initial screen though, we only had about a 2-to-1 selectivity, and the catalyst did not respond to modifications particularly well. A series of other popular or commercial bases or superbases were also tested, for example these hydrogen bonding donor-containing cinchona alkaloid-derived bases, but they did not prove effective in this reaction. Similarly, many phase transfer conditions in chiral cations were not able to induce very high levels of selectivity for this reaction in our hands. The turning point of the selectivity part of this project was when we attempted the cyclization using an iminophosphorane catalyst. This class of catalyst was pioneered by the group of Darren Dixon at Oxford and merges an ease of preparation from azides and phosphines and ease of tunability. So finally, with the selectivity hit in our hands, of course we got inspired by the Dixon group and their evolution of this catalytic system over the years to try to improve our system into high levels of selectivity. And after a couple of generations of catalyst optimization, we were able to finally land on this squaramide-based catalyst as the most selective for our transformation, which made us break the barrier of the 9-to-1 selectivity. The notable features of the optimization are the presence of a second amino acid on the left portion of the catalyst, a squaramide in place of the original thiourea, which heightened the reactivity of the catalyst, and a much more bulky phosphine that was beneficial for selectivity. At this stage, we wanted to explore the scope of the reaction, and optimization substrate, under the final conditions, was obtained in 88% yield and 92.8 ER. Substitution of the peripheral rings tended to be well tolerated, with this chloro-substituted substrate achieving the highest levels of selectivity for this system, 94.6. Substitution of the methyl blocking group on the right-hand side of the molecule for a chloro group was more detrimental for conversion, presumably because we now weakened the nucleophile with electrostatic effects. On the other hand, while peripheral substitution seemed to be well tolerated, internal substitution off of the amide nitrogen and off of the sulfonamide was detrimental for selectivity, although reactivity was retained. We believe this has to do with the mode of interaction between the catalyst and the substrate, which we will discuss in a minute. Notably, we were also able to access this highly congested orthonitro-substituted product in high yields and selectivity. Given the challenges of synthesis of highly congested dibenzazepinones, we believe this is a quite remarkable result. Lastly, we would like to highlight some limitations of the protocol. For example, the presence of the methyl blocking group on the right-hand side of the molecule does not only have to be present for configurational stability reasons, but also pre-organizes the nucleophile towards intramolecular attack. In fact, we were able to get no conversion if that blocking group was on the left-hand side of the molecule. Under a slightly more forcing condition, this substrate would only lead to intermolecular selectivity and not intra. We also synthesized a substrate which did not have any methyl blocking group and found that while chirality was retained, the conversion was much slower, presumably due to, again, an effect of pre-organization induced by the methyl group. Analogously, we prepared a substrate containing a vinyl chloride group conjugated to the left ring amide group. This did not lead to any intramolecular reactivity, as we expected, because the vinyl chloride is not conjugated with the amide due to the intramolecular reaction, but only led to intermolecular reactivity under more forcing conditions. At this stage of the project, we wondered if we could pour the strategy on two different systems, perhaps even mechanistically different systems, given that we are preserving all the strategies that enable these reactions to go. For example, what if we feature a longer link between the reacting groups, still achieving perhaps a cyclization of a ring that features inherent chirality due to steric clash of some of the substituents? So for example, what happens if we replace the nitroaryl fluoride group for a benzyl chloride? Would we be able to pour the same reactivity towards an intramolecular SN2 reaction that can be mediated by the same basic catalyst? In the end, the conformational pre-organization of the tertiary amide is still in place, and we expect the catalyst to be able to interact with similar functional groups, perhaps in a similar manner, to induce enantioselectivity in this system as well. And I'm happy to say that this approach also played out quite well, and under very similar conditions, we were able to induce the same reaction to form inherently chiral 8-membered rings mediated by the same iminophosphorane catalyst. In fact, these played out even better in terms of selectivity. The reaction was faster and enabled us to cool it down to -20°C to enhance the selectivity we were getting at room temperature. I would note that potassium carbonate is used here instead of calcium oxide, since we're not dealing with fluorides anymore. Substitution of these rings was also well tolerated and enabled us to prepare a series of derivatives in high yields and high selectivity. The most observant of you might have noticed that I've drawn the two rings in different ways, and this is because we found out we were making opposite enantiomers of these two ring systems. Initially, this was quite surprising for us because the initial premise for trying the 8-membered ring was that the catalyst would have had the same types of functional groups and overall geometry and stereoelectronics of the system to induce selectivity in a similar fashion, and therefore we expected the same enantiomer to be formed for both ring systems. But both DFT and X-ray crystallography hinted that we were making the opposite enantiomers of these two cups. So why is that? If you look at the DFT models for these reactions, you can see that, for example, in this SNAR example, the transition state assembly is mainly governed by hydrogen bonds between the central squaramide and the sulfonamide nucleophile, but maybe less evidently, and this is true for both the transition state leading to the minor and the major enantiomer, there is a degree of dipole minimization between the substrate and the catalyst. This is because the partial dipole of the substrate is directed towards the nitroaryl ring, while the dipole of the catalyst is mainly oriented in the opposite way, due to the positively charged phosphonium cation on one end and a lack of charge on the other side of the molecule. Another way to look at it would be that the accumulation of the negative charge on the nitroaryl ring is spatially close to the positively charged phosphonium ion. And you can imagine that these general observations are also true for the 8-membered ring system, where we observe both hydrogen bonding and overall dipole minimization between the catalyst and the substrate. Although I will note that this hydrogen bonding network is now different, also because it favors the opposite enantiomer of the cup-shaped ring relative to the 7-membered rings. And if you're asking, well, where does selectivity come from then, and why does it enantiodiverge between the two ring sizes? We've done some energetic decomposition of these computational data, and we think that the best explanation is that it correlates with the dispersion energy between the different diastereomeric transition states. So in other words, the dispersion energy donor groups on the phosphine ring, in this case the tributyl groups, are not only beneficial for selectivity, as we had observed during the optimization, but are also perhaps responsible for enantiodivergence by adapting differently to the different ring sizes. If you're interested in technical details of these decomposition and the magnitude of the different components, I suggest you check out the paper and the supporting information, which contain many more details and are publicly available. Lastly, I will highlight the stereochemical stability of these ring systems, because the 7-membered rings showed a very remarkable degree of stereogenic stability, and refluxing them in toluene overnight produced no erosion of their enantiomeric purity, and therefore their inversion energy is at least 36 kcal per mole. On the other hand, 8-membered rings have lower enantiomerization energy, and their racemization can be followed by HPLC at 75 degrees. Interpolation of this data enables us to estimate the interconversion energy to about 27.5 kilocalories per mole, corresponding to a half-life at room temperature of around 200 days. The stability of these systems of course correlate with the size and the nature of the blocking group that are causing the fundamental clash that locks these compounds in one configuration. But already with a methyl group, we have an interconversion energy that would allow their development as single stereoisomers in medicinal chemistry campaigns. In conclusion, we have developed a mild protocol for the cyclization of inherently chiral medium-sized rings, with a catalyst that shows generality across different mechanistic paradigms and different ring systems, and surprisingly gives different enantiomers of different products. I would also like to acknowledge my advisor Scott Miller for the freedom to explore this project, and all of the members of the group, past and present, with which I overlapped and I'm still working with. Special mentions to Dr. Brandon Mercado for being an excellent crystallographer, and to the Yale Center for Research Computing, which provided the resources to run all the computations of this work. I also acknowledge funding from the Kenneth Weiberg Fellowship in Chemistry from Yale University. If you want to connect with me, I also left some handles for the lab and the personal accounts on some social media platforms. Thanks again for the opportunity to present my work, and to everybody involved with the synthesis workshop to enable us to be exposed to such exciting chemistry.
Thank you, Nicolò, for the interesting work about the enantiocontrolled ring synthesis. If you enjoyed the episode, feel free to subscribe our YouTube channel and follow us on Twitter. Thanks again, and hope to see you in the next talk.